Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 30 on simple areas.
As we begin Chapter 4 of the course, we're going to turn from our classical tools of Taylor series, limits, derivatives, and integrals, and begin putting them to work. We'll focus on applications of the definite integral, beginning with some simple area formulae. We'll start small, but work our way up to bigger things.
You might think that when computing areas, there are a lot of formulae that you need to memorize. Well, fortunately, that's not the case. There's one formula that you need to know for area, and that is that area is the integral of the area element, dA. What do I mean by that? Let's recall some of the classical area formulae that you learned when you were in school. The area of a rectangle, or a parallelogram, or a triangle, or a circular disk. These you know, but do you know why they're true? They're true because they are the integral of the corresponding area element. Let's see how this works in a few examples. Recall a parallelogram. Now, you would probably argue by rearrangement that if you cut into pieces and reshuffle, then you can build a rectangle, and we all know the area of a rectangle. Well, that's good, but there's another way to think about this. Consider your parallelogram in the xy plane with the base on the x-axis, and then slice it into horizontal strips of, if you will, an infinitesimal thickness, dy. Then what is the width of each strip? It is, let's call it b, the length of the base of the parallelogram. Now, how do we get the area out of this? The area element, the area of this thin strip is, well, b times dy. Thinking of it as a rectangle with one edge of infinitesimal length. The area is the integral of the area element. That is the integral of b dy as y goes from 0 to h, the height of the parallelogram. And now let's see how it falls out. The integral of a constant dy is that constant b times y. Evaluate from 0 to h, and we obtain simply b times h, which we all know is the area. Now, there's a slightly different perspective we can put on this, namely that when we shear that parallelogram and slide the horizontal slices so that it becomes a rectangle, then we are not changing the area element. This shearing preserves the area element, and thus the area. That's a different sort of rearrangement argument, one at the infinitesimal level. This also helps us make sense of the area of a triangle. You're probably used to thinking of it as half the area of the bounding rectangle by using geometry and similar triangles, but we could do things a little bit differently if we also arrange this triangle so that the base is along the x-axis and shear it horizontally so that it becomes a right triangle. We see we have not changed the area since we've preserved the horizontal area elements. Now, the hypotenuse has the equation of y equals h over b times x. Now let's consider a slightly different area element, this one vertical. The height of that vertical strip is going to be, from our equation for y, h over b times x. The thickness is dx. And thus, computing the area as the integral of the area element, what do we get? We get the integral of h over b x dx as x goes from 0 to b. And now, what do we see? Well, h over b is a constant. X integrates to x squared over 2. Evaluating from 0 to b gives hb squared over 2b minus 0. Simplifying, we get 1/2 base times height. Very simple.